Good day, students. Today, let us look into a phenomenon exhibited by light, that is polarization of light. This is a straight proof of the transverse nature of light. The pictures shown here show the difference in images using polarized light and non-polarized light. Here, in these two pictures, this picture shows the reflected light, whereas in this, the reflections have been removed. This is because of using filters or Polaroids during the photography. Again, in this image, here, in this image, we cannot see the rocks beneath the water level, whereas here, by removing the reflections from the surface of the water, we can see the rock structures below water. Again, here in these two images, we can see there is a difference in depth of the image, in the color of that blue light. So by using Polaroids or by using polarized light, we can get clearer images. Now let us define what is polarization of light. It is the phenomenon of confining the vibrations of a wave in a specific direction perpendicular to the direction of wave motion. And this phenomenon is called polarization. First, let us see what is unpolarized light. Now, light is an electromagnetic wave as shown here, in which the electric and magnetic field vectors vary sinusoidally, such that they are perpendicular to each other and as well as perpendicular to the direction of propagation of light. Okay. Now, the electric and magnetic fields are varying sinusoidally and they are perpendicular to the direction of propagation here, x. In ordinary or unpolarized light, that is light emitted by the sun or any bulb, incandescent bulb, the vibrations of the electric field are in all possible directions perpendicular to direction of propagation of light. Okay. So if x is the direction of propagation, the electric field vector can vary in different axes across y, right? And this is represented by this picture here. It can also be represented in terms of this picture here, where we have vertical lines, vertical arrows and dots at the center. Okay, so if the direction of light propagation is in this direction, the direction of the light vibration is either in the dotted or in the vertical lines. And this representation is used for unpolarized light. Now, plane polarized light. For that, what do you mean by the plane of polarization? The plane containing the direction of vibration and direction of wave motion is known as the plane of polarization. Okay, so regarding the earlier figure, it is the XY plane. Plane polarized light is the light whose vibrations, or specifically its electric field oscillations, are confined to a single plane. It is perpendicular to the direction of wave motion and it is called the plane polarized light or linearly polarized light. Here we speak in terms of electric field because we have a relation E electric field vector is equal to C times B magnetic field vector. So the stronger vector here is the electric field. Now in this picture we can see that when unpolarized light having random polarizations, electric field vector can change across the y-axis in any direction. So if this randomly unpolarized light is incident on a Polaroid or a filter or a polarizer, its transmission axis is in this direction, in the y-axis direction. This polarizer will allow only those polarizations or only those electric field vectors that are parallel to the transmission axis. And hence we can see only that electric field vector is passing through. Hence, we can say that the electric field vectors are confined to the XY plane and we get linearly polarized light. Here, the plane polarized light or linearly polarized light is represented in these two methods, either by the vertical arrows or by the dots. The dots represent that the vector is into the plane or surface, whereas the vertical arrows represent that the vector is along the plane or surface. Now, when unpolarized light is converted to plane polarized light, its intensity will decrease by half. And polarization is a convincing proof of transverse nature of light. Now, in transverse nature of light, we define that field vectors are vibrating perpendicular to the beam direction, right? Now, only because of this difference is that we are able to confine the electric field vectors into one plane. If light was longitudinal wave, its oscillations will be along the beam direction, and hence we won't be able to confine the different electric field vectors. So by polarization, we have proved that light is a transverse wave. Our eyes cannot distinguish between polarized and unpolarized light. Hence, we use other optical elements like polarizers or Polaroids to distinguish between it. Crystals like calcite, quartz, tourmaline, and nickel prism can produce plane polarized light, and they can analyze light. So if we pass randomly unpolarized light through these materials, we can emerge plane polarized light from it. So it becomes a polarizer then. And if we have an unknown source of light, we don't know about its polarization. If we pass that unknown source of light through it, we can check whether this light is polarized or not. And at that time, these materials are used as analyzers. Now, let us see what are the different methods that can be used for polarizing light. First, polarization by reflection. Now, when unpolarized light, randomly polarized light is falling on any surface, okay, at any angle, the reflected light can be partially polarized, it can be completely polarized, or it may be completely unpolarized. Okay. Now, at a particular angle, if light is incident at a particular angle, the reflected light will be completely polarized. And that angle is called the polarizing angle theta b. Okay. So the angle of incidence at which the reflected light is completely polarized is called polarizing angle theta b. It was Sir David Brewster who proved that the tangent of the angle at which polarization by reflection is achieved is numerically equal to the refractive index of the medium. He stated the mathematical principle that the refractive index mu is equal to tan of theta b, and this is called Brewster's law. Here we see that when light is incident on a surface at the polarizing angle theta b, the reflected light is completely polarized and refracted light is partially polarized. The angle between the reflected ray and refracted ray will be 90 degree. Hence, we can say that this angle, okay, so that is 90 minus theta b, and this angle, that is 90 minus r. So we get this angle. 90 minus theta b plus 90 minus r is equal to 90 degree. From that, we get theta b plus r is equal to 90. Now, by Snell's law, we have the refractive index of the medium is equal to sine I by sine r. Now, when light is incident at polarizing angle theta b, the angle of refraction will be 90 minus theta b. So, Snell's law becomes mu is equal to sine theta b divided by sine of 90 minus theta b. That is sine theta b by cos theta b, that is equal to tangent of theta b. Hence, we prove Brewster's law. Now, if light is incident at the polarizing angle of 56.3 degree on a glass sheet, the reflected light will be completely polarized. And if we know the polarizing angle, we can calculate its refractive index by mu is equal to tangent of 56.3 degree. Now, Brewster angle can be utilized to find refractive indices of opaque materials, remove reflection losses in lasers, remove reflection losses in optical fibers. These are just some of the uses. Now, the next method to produce polarized light is by refraction. Now, here we saw that when light is incident on a surface at polarizing angle, the reflected light will be polarized. But the refracted light will only be partially polarized. Okay. So now if we do multiple refractions in this purpose, the emergent ray that is finally emerging will be completely polarized. So if we take a pile of 20 to 30 glass plates and light is incident at the polarizing angle 56.3 degrees, the transmitted light after multiple transmissions from these 20 to 30 glass plates will become plane polarized light. Here we have the figure of the pile of plates, and hence after multiple refractions, the emergent ray will be plane polarized light. Now the next method of producing polarization is by using Polaroids. Now a Polaroid or a polarizer is an optical filter that filters the unpolarized light to produce plane polarized light. So here what happens is, if we have unpolarized light, the electric field vector is varying randomly. It is passed through this Polaroid or polarizer, and only those electric field vectors that are parallel to the transmission axis will be allowed to pass through. And hence, while confining the electric field vectors, we get plane polarized light. Now here in this figure, if we see, we have randomly polarized light or unpolarized light passing through a Polaroid, and hence we have linearly polarized light in this direction of polarization. Again, if we pass this linearly polarized light through another Polaroid, which is oriented along the same axis of transmission, the same light can be seen to pass through. Now, if we tilt the second polarizing filter or second Polaroid, here it is called the analyzer because it analyzes the incoming wave. If we tilt it at an angle theta, the intensity of emergent light will decrease because it will only allow that component of electric vector that is parallel to this transmission axis, right? So this vector E, it will be resolved into two components based on this analyzer, and only that component that is parallel to its transmission axis will be passing through. Now, when this analyzer is rotated 90 degrees with respect to the polarizer, no light will pass through it. We can observe it using this figure. Here, let us use this ring as the first polarizer and the second filter as the analyzer. Now, if we have random light here, if we use a polarizer and view the random light, the intensity is reduced by half. Okay. Now, we are using an analyzer and rotating it to verify whether the light coming from the polarizer is linearly polarized. So at 0 degrees, we have the same light intensity. As it is 90 degrees, its intensity becomes 0. Again, at 180 degrees, its intensity becomes maximum because transmission axis is in that direction. Again, at 270 degree, since the transmission axis is in this direction, the intensity will be minimum. Okay, so we can verify that the incoming light ray from the polarizer is plane polarized light. Now, we can measure the intensity of light emerging from a Polaroid. When plane polarized light of intensity I0, that is equal to Ke square, is incident on a Polaroid at an angle theta, The Polaroid will pass only those components of vibration that are parallel to the transmission axis. That is, it will pass only the E cos theta value, right? So if we have plain polarized light in this direction, okay, it is falling on an analyzer, it will allow only this component that is parallel to the transmission axis to pass through. That is E cos theta. Hence, the intensity of the emergent light I will be proportional to E cos theta square, that is equal to K E cos theta square, that is equal to I0 cos theta square, where I0 is equal to Ke square. This is called the Malus law. Now, when unpolarized light is incident on a Polaroid, the emergent intensity will be the average intensity. So if we take the average value here, I average, here it becomes the average of I naught cos square theta. Since I naught is a constant, it comes outside, and the average of cos square theta is 1 by 2. Hence, I average is equal to I naught by 2. Thus, the emergent light intensity is reduced by half. Let us see what we mean by optically isotropic materials. These materials exhibit the same index of refraction in all directions. So if light passes through it, light will refract as a single ray. And the examples for that are glass, water, air, table salt, etc. Now, we also have optically anisotropic materials. Now, these materials have different index of refraction in different crystallographic axes. Okay, so if light passes through it in one direction, it will show light refracting as two beams. But when light passes through it in another axis, it will again show a different form of refraction as two rays. Now, the refraction of two rays is called double refraction, and the materials exhibiting it are calcite, this is calcite, calomel, ice, quartz, sodium nitrate, tourmaline, ruby, etc. Now, we have uniaxial and biaxial crystals. Uniaxial crystals are anisotropic crystals that show double refraction and have two perpendicular polarizations, two refractive indices, and one symmetry axis. That is, when light passes through it, light will refract into two rays. One is called the ordinary ray, O ray, and the other is called the extraordinary ray, E ray. The O ray sees the refractive index mu O, that is ordinary index, and E ray sees the refractive index mu E, ordinary index. The O ray will obey Snell's law of refraction, whereas E ray does not obey the Snell's law of refraction. Okay. So when light passes through these uniaxial crystals, it will refract into two rays. Okay. But at a certain angle, at a certain axis, when light falls through it, both the rays will travel as a single ray. That is called the symmetry axis. And these materials or these crystals have one symmetric axis. Examples for uniaxial crystals are ice, quartz, calcite, tourmaline, ruby, calomel, etc. Now, in biaxial crystals, they are anisotropic crystals that show double refraction, and they have two perpendicular polarizations. They have three refractive indices and more than one symmetry axis. In this, light refracts through it as the fast ray and the slow ray, and both rays do not obey Snell's law of refraction. Biaxial crystals are Epsom salt, borax, mica, topaz, etc. Now, double refraction, also called as birefringence, is an optical property in which a single ray of unpolarized light enters into this anisotropic crystal and it splits into two rays. Both the rays will be traveling in different directions. So here we can see that when unpolarized light falls on a birefringent material, birefringent crystal, it refracts into two. It refracts into the ordinary ray and the extraordinary ray. And the ordinary ray will be plane polarized in one direction, whereas the extraordinary ray will be plane polarized in the other perpendicular direction. Okay, so in effect, we can get polarized light from it. Here in this calcite crystal, we can see that this line, when observed through this crystal, will be seen as two lines, right? And the written alphabets, calcite again is here appearing as two sets of letters. This is due to the formation of two rays, O ray and E ray. Now here in this video, we can see the formation of these images by the two rays. We are placing a Polaroid on top of it to view either one of the images. By tilting the Polaroid, so we will see one polarized light at one time, and at the other angle we will see the other polarized light. Now Huygen explained double refraction. In his explanation, he said that when light falls on an isotropic material, the light then spreads as a spherical wavefront through it, because light sees the same index of refraction on all directions. Whereas when light falls on an anisotropic crystal, it will see different refractive indices in different directions. In particular, for a uniaxial crystal, it will see two refractive indexes, and it will separate as the O ray and the E ray. Now, the O ray will propagate with the velocity VO and in the refractive index mu O, whereas the E ray will propagate with the velocity VE, seeing the refractive index mu E. Sometimes the velocity of the O ray will exceed the velocity of the E ray, and in those materials we get this pattern here. Here we have plotted the wavefront of the O ray and the E ray. So the O ray will travel faster than the E ray, and this crystal is called the positive uniaxial crystal. But in other cases, sometimes the O ray will travel slower than the E ray, and hence the wavefronts will be of this pattern where the O ray is enveloped by the E ray. So let us discuss in detail what is positive and negative crystals. Positive crystals are anisotropic crystals in which the change in refractive index of the two rays is positive. That is, delta mu, mu E minus mu O is positive. It means that the refractive index of the E ray is greater than the refractive index of the O ray. Since refractive index is inversely proportional to the velocity of the ray in the medium, we have velocity of E ray is less than the velocity of the O ray. And hence we get the wavefront pattern as shown. Examples for positive crystals are ice, quartz, and calomel. Now in negative crystals, they are anisotropic crystals in which the change in refractive index of the two rays is negative. That is, delta mu, that is mu E minus mu 0 is negative. It means mu E is less than mu O. So the velocity of the E ray will be greater than the velocity of the O ray, and the nature of wavefronts will be as shown. Examples for negative crystals are calcite, tourmaline, and ruby. We can polarize light by double refraction. So here, by double refraction, we can separate the O ray and E ray. Further, isolating one ray from the other, we produce plane polarized light. This is achieved in nickel prism. So here, when unpolarized light is falling on nickel prism, it separates into two by double refraction. Here, this separating layer is Canada balsam, and it will internally reflect the O ray, whereas E ray can transmit through it. The surrounding surface will be blackened, hence O ray will be absorbed towards the surface. We can see the surrounding is blackened, and it allows only E ray to pass through it. Thus we get plane polarized light by double refraction. So today we have seen what is polarization of light, what is plane polarized light, and what are the different techniques by which we can achieve polarized light. That's all for today. Thank you.